this. He. I have sent his talk.
No, it is not.
What they talk?
Murthy and
Murthy and I just sent something like this. Last week, day 5. Yeah.
see that.
Okay. Good afternoon. So we'll start our last session of this conference. So before I start, I would like to inform you that we'll have a special evening talk today at 5:30 by Professor Mangal Sundar from IIT Madras. Okay, thank you. Okay, it is about NPTEL. Yeah.
What is NPTEL? Oops. Okay, so we can start the next session. So we're pleased to have Professor Murthy from Math Science. He's going to talk about a decade of discovery and beyond neutrino physics.
Yeah. I was telling him that it's a one-street village, somewhere between Mysore and Coorg on the way to Markara. And since nobody knows the name and it is not on the map, I thought I should let it be known that there is a village like that. Yeah. So, thank you very much for inviting me to talk about this subject in this celebration of 100 years of quantum mechanics. I'm not very up to date nowadays, so it will be a bit dated, the information. But nevertheless, I thought I will try to cover this decade of discovery and beyond and come all the way to the contributions from IMSc. So it will be incomplete because given the time, I will not be able to talk about everything in great detail. So it will be a very broad brush, and I'll try to go through a bit of history and some important observations, and then come to IMSc contribution and some selected papers that we wrote from IMSc I will review, and some open problems and future possibilities I will talk about in the end. So, I called it decade of discovery from 1930 to 39 because just as the previous decade where quantum mechanics, it really happened at great pace, similarly things related to neutrino physics, many important ideas and discoveries happened within a matter of 10 years. And even today, we are actually processing many of those ideas. So I think it's important to know what happened in a certain chronological sequence. And of course, most of you know that there was this problem of continuous spectrum in beta decay. So what was observed was that there was a decay of a nucleus to a daughter nucleus, and there was an electron that was emitted. This is what was observed. And if it was a two-body decay, then electron would have been monoenergetic in the sense that it would come with a well-defined energy. What they found was a continuous distribution of this electron energy. It's called as the Curie plot. And there was a problem. So if there is this continuous energy, then there has to be something else in order to satisfy conservation of energy. And later, of course, we also knew that you could not have conserved angular momentum, so there had to be a particle which carried the rest of the energy as well as the angular momentum. So Pauli made a bold proposal that there must be an extremely light neutral particle which is also, he said, which is also part of the nucleus in 1930. And initially Pauli called it neutron, and then later on Amaldi and Fermi named it as neutrino, because between those 2 years neutron had been discovered just after the proposal for neutrino. This happens to be one of the last great contributions of Pauli, after which he faced many personal problems, and it took many years for him to come out of it. And later in the 1940 he came out with the spin statistics theorem, and there was also one more very important thing Pauli contributed, which is the Pauli-Villars regularization. That was after the quantum field theory ideas came about. But nevertheless, it's a very brave thing for Pauli to propose a particle, because during those days it was not very common to talk about new particles. In fact, electron had been discovered in 1897, photon in 1905, and proton in 1917 by Rutherford, and theoretically positron was predicted by Dirac in 1927 and detected in 1932, and then the anti-neutrino proposal came from Pauli. So it took a long time to confirm this theoretical proposal of Pauli. And in 1933 Fermi formulated the theory of beta decay, and we know that it's the theory of weak interactions, which began from Fermi's work, as distinct from electromagnetic and nuclear interactions, which were known just before that. So there was immediately a flood of ideas and experimental results which followed this. So within a year of Fermi's work, Irene and Frederick Curie observed beta plus decay, in which a neutrino is emitted instead of an antineutrino. And in 1934, Wick proposed the electron capture or the inverse beta decay, and that was immediately observed by Alvarez in 1937. And then interestingly, in 1935 itself, Maria Mayer proposed the possibility of double beta decay, where a nucleus goes into a daughter nucleus emitting 2 electrons and 2 antineutrinos. And this took a long time for observation. So since 1987 we have been seeing examples of this neutrino, 2 neutrino double beta decay. Importantly, in 1937 Ettore Majorana noticed that this neutrino is a fermion and is neutral, and is the only neutral fermion even in the SM, and that may be its own. He proposed that it may be its own antiparticle. So then the question comes, is it a Dirac type particle where neutrino and antineutrino are distinct, or is it a Majorana type particle whether neutrino and antineutrino are the same? So this is one thing, this is still an open problem. I will have some time to comment about it. And immediately following Majorana's suggestion, Furry proposed neutrino-less double beta decay as opposed to 2 neutrino double beta decay as a signature of neutrino being a Majorana particle. If neutrino is a Majorana particle, then you must observe this neutrino-less double beta decay, but we don't know the rate and other things. So it has not yet been observed, and experiments are still going on. So, but there are clear alternatives possible for the present experiments which are going on. If there is time, I will talk more about this. Majorana, incidentally, was considered a genius on par with Galileo and Newton by Fermi. In fact, he states that in one of his letters, mysteriously disappeared at the age of 31 or 32 on 25th March 1938 while traveling from Palermo to Naples in Italy. There are a lot of stories surrounding this disappearance. Some people think that he didn't die, and some people think that he reappeared in Venezuela or in some other place, but there are a lot of stories which one can read online. Now, after this landmark things, the last of the things in the 30s decade is Bethé's work on solar neutrinos, but that I will talk in a little more detail after a couple of slides. So many landmark events happened towards the completion of the standard model of particle physics immediately after this first decade. In 1956, Reines and Cohen detected neutrinos, actually antineutrinos from the reactor, and same year C.S. Wu confirmed the parity violation proposed by Li and Yang a year before. And in 1957, Sudarshan and Marshak proposed the V minus A theory of weak interactions, and it was also proposed by Gelman and Feynman, but I think the priority wise it should be Sudarshan and Marshak. And in 1958, Goldhaber did, it's actually called a beautiful experiment. He did an experiment to determine the helicity of the neutrino, and it turns out that, at least from this experimental result, you tend to think of neutrino as left-handed, as a chiral eigenstate. And this is what led to the massless neutrino dogma, and that is part of the standard model even today. Nevertheless, around the same time, Pontecorvo proposed the neutrino-antineutrino oscillations in 1958. He was inspired by the KK bar oscillations, and using that idea, he said because neutrinos are neutral, neutrino-antineutrino oscillations could in fact happen. Of course, it violates lepton number, and therefore it is beyond the standard model. But the idea came in 1958 itself, and in 1962, Lederman et al. Discovered the muon neutrino. However, tau neutrino discovery had to wait till the beginning of the 21st century. So now we have 3 active neutrinos, all of them have been detected: electron neutrino, muon neutrino, and tau neutrino. So with that, we have this periodic table of the standard model. There is a family of leptons. There are 3 flavors: electron, muon, and tau. Corresponding to each one of them, there is an electron neutrino, muon neutrino, and tau neutrino. So these are 3 families, flavor families, and you have also these gauge bosons and the quarks, and of course the Higgs field which connects all of them. And in this periodic table, the mass of the neutrino is strictly 0. So let me go back many decades and come up to Bethé's work and later experimental discoveries. This is the question of stellar energy production. The question of what powers the sun is a very old question, and of course if you go to centuries before, there have been many speculations. In fact, every culture had its own theory of how the energy is produced in the sun. But in 1860, a serious debate started on the origin of the solar energy, and this was between Darwin and Kelvin. Darwin, for the evolution, on the basis of the evolution theory that he had, in order to produce huge variety of living organisms and species that we find today, he said that it could have taken at least 300 million years for many of these things to evolve. So he needed a minimum of 300 million years of energy available on Earth. And the main source of energy available on the Earth is sun. So therefore, sun would have been shining for more than 300 million years. So therefore, the energy source of sun must be enough that it would last at least 300 million years, if not more. But then Kelvin calculated the gravitational energy or gravitational potential available on the sun, because we know the solar mass, and from that and of course we know gravitational constant G, so that gave him a figure of 30 million years. So sun could not shine just with gravitational energy alone more than 30 million years. This is actually a simple back of the envelope calculation, and it can be done very easily. So so obviously there was a contradiction between what Darwin required and what Kelvin said. And in fact, both were right in their own way, and one had to look for new sources of energy, because gravitation alone could not have sustained the sun for such a long time. So there were hints of new energy sources. For example, end of 19th century, you had radioactivity, and in fact Rutherford first thought it should be radioactivity, but it was not to be for various reasons. At this time, around in 1920 or so, Eddington wrote his prophetic paper, Internal Constitution of Stars. This is a very important paper in astrophysics. So where he showed that the mass of helium atom, which is about 0.8% less than the mass of 4 hydrogen atoms, which when combined form the helium atom, the difference is about 0.8% and it's less. So therefore, he suspected that the emission of this difference could be the source of energy that is produced in the sun, and he made a calculation that even if 5% of hydrogen, and most of sun is hydrogen, is converted into helium, that would suffice to power stars for a very long time. And many other elements could also be fused, and therefore the interior of stars is a crucible for all elements found in the universe. Eddington's speculations were proved to be true, and in the following decades details were worked out by Bethe, which gives the possible duration over which the sun shines as about 9.5 billion years, and at present sun is middle-aged, 4.5 billion years old. So we still have 4.5 billion years to go for the sun to end its energy production cycle. Eddington not only speculated on this, he said that this fusion, which is giving so much energy, can either be used for the benefit of the mankind or the complete destruction of the mankind. I think the second part of this statement is something that we have already realized, that all these bombs and other things are going around. So the details of ideas floated by Eddington were worked out by Bethe. Before Bethe, there were some ideas in the work of Gamow and Weizsäcker, and they propose a set of chain reactions, PP chain, as the energy production mechanism. Bethe also worked out another mechanism which is called as the CNO cycle, but it is now known that it is the PP chain that is mainly responsible for the energy production in the sun. The important thing to notice in PP chain is that it starts with weak interaction process, PP going to 2H plus E minus nu E. And this is called as the PP neutrino, and then the neutrino is also emitted in the beryllium interaction here, and also in the PEP, and there is one which is 8 boron reaction, there also a neutrino is emitted. These are all electron type neutrinos. And so if this is a theoretical proposal, if you want to prove this theoretical proposal that fusion as the basis of energy production, you must discover these neutrinos. These neutrinos are produced exclusively in these fusion chain reaction, whereas light can be produced by many other processes. So the proof of the pudding, that is this proof of this fusion, is really in detecting these neutrinos, and this was completed in this paper by Bethe and Critchfield, and later by Bethe in March 1939. So the details of these flux calculations from these processes, putting in inputs of the nuclear reaction rates, amount of mass that is undergoing this fusion, that means the core mass that is available where the pressure and density is high enough for the fusion to proceed, taking in all those into considerations, in 1964 Bacall came up with what is called as the standard solar model. And in the standard solar model, you have the flux from various processes, flux of neutrino calculations from various processes. Mainly, there are what are called as PP neutrinos, which I showed in the previous one, then the 8 boron neutrinos and the HEP neutrinos. These colored ones are the ones which are most important, and there is also a monochromatic, monoenergetic neutrino, this comes from another process which we saw earlier here, the beryllium, 7 beryllium. So now that we know this flux, there must be a way to detect these neutrinos. And that's rather hard because neutrinos interact very weakly. Yeah. Here?
Nitrogen, oxygen, and
Yeah. These are coming from the CNO cycle. The dashed line neutrino fluxes are calculated from the CNO cycle. It's not very important for the energy production, but the neutrinos are produced also in the CNO cycle, and they come. The dashed lines are from the CNO cycle chain, and the solid lines are from the PP chain.
And another very naive question I had. So in the nucleosynthesis that happens in the early universe, those are more strong interaction driven, not the weak interaction ones.
I would think so, but I haven't looked at it.
In the nucleosynthesis process that happen in the early universe, those are more driven by strong interactions, right? Or is it?
The very first reaction is this.
Okay.
And as I said, 4 protons can't come together. Sorry, 4 protons don't come together to form an alpha or anything like that. So it is this process. But what happens is in, next generation stars, then all this material goes, and then there are fusion reactions with, synthesized silicon, magnesium, and stuff like that, all the way up to iron. Then it stops there. Then, unless there is a explosion, a supernova explosion, or a neutron-neutron star collision, you don't produce the still heavy element. Because for that, you need neutrons.
Actually, the sequence, you can see a combination of processes. Electromagnetic is also there. Nuclear is also there, and weak interaction. But the trigger is weak interaction.
No, not strong interactions. See
There are some
the
strong.
fusion.
Helium-3 is a strong interaction.
There's a nuclear interaction.
Going to helium-4 and 2p.
Yeah.
So
There, of course, yeah,
there
that,
is a few like that.
yeah, few,
But
okay.
it's,
Primarily, it is electromagnetic and weak
Primary.
interaction. Yeah.
And that's how the sun actually shines slowly. It's like a slow medicine that seeps into your blood. It's like that.
In fact,
had
that's
it
what
been electromagnetic, we would not have had time to evolve.
That's the thing I wanted to say.
happen very fast.
In the nuclear fusion bombs,
Yeah.
that is DT strong fusion.
Yeah.
That's why it happens so fast.
Yeah.
Otherwise, your nuclear bomb, if it is exploding over billions of years.
Yeah, but the trigger is the weak interaction, the PP.
That's right.
So there are also some lines here shown. These are actually the detectors: gallium detector, chlorine detector, and Kamiokande detector. I'll talk about them a little bit. But what it shows is the threshold beyond which they can detect the neutrinos, the neutrino energy threshold beyond which they can see them, they can detect them. Okay. So the detection, Ray Davis was the first one to detect solar neutrinos. In fact, he was interested in detecting solar neutrinos from 1948 onwards. There are many lab notes by Davis in which he considers all kinds of ideas. And then Bakal in around 64 or so suggested the new interaction with chlorine 37 to 37 argon and E minus. This has a threshold of 0.814 MeV, and the experiment was then mounted at Homestake mines at a depth of about 1.5 kilometers, a tank filled with C2Cl4. So chlorine, the dominant isotope is 35 with an admixture of 37, and therefore C2Cl4 provides the target, 37 chlorine, and the expected rate was about 7.5 plus or minus 3 SNU in that detector, and the observations recorded only about 1/3 of the expected results. So this gave rise to what is called as the solar neutrino puzzle. So we have detected neutrinos from the sun, but then we are not detecting enough neutrinos from the sun. There is a deficit. But then this experiment has some limitations because this argon counting has to be done over a period, because you have to collect enough number of argon atoms, and they can be flushed out by flushing helium gas through this liquid. They get attached to each other, and then you bring it out. Argon gets attached to helium.
That was Alvarez's idea.
Yeah, correct. So then they count the argon atoms after a few days, and this has a lifetime of close to a month. So therefore you can wait for a few days, but then it's not a real-time experiment. It is also, there is no energy measurement. What you know is only the total rate. So how do you know these are from the sun? Though there is no other source which can give so many events, you have to show that it's actually from the sun, looking at the direction and also measuring the energy. So that so maybe we can find answer to this solar neutrino puzzle if we have such an experiment. So such an experiment, by the way, these radiochemical experiments, better experiments were done at Galax and SAGE, which had lower threshold. So therefore they had more number of events compared to what Davis had, but still there was deficit. Let me not go into the details of the deficit. So Kamiokande was launched in Japan in 1983. The main aim of Kamiokande was to study proton decay. In fact, it's Kamioka nucleon decay experiment. That is how the name comes. The main background for the decay events, for proton decay events, are the neutrino events at a depth of, and the experiment was mounted at a depth of 1000 meters. And the detector consisted of 3 kilotons of ultra pure water surrounded by 1000 photomultiplier tubes. So whenever this electron neutrino interacts with the electron in this water, then it will scatter, and the knocked out electron gives out the characteristic light, the Cherenkov light, which was seen by these photomultiplier tubes. But in order to emit Cherenkov lights, these electrons have to be relativistic. So therefore this had the limitation that they could only, initially they could only see neutrinos above 7 MeV or so. So this then they made an improvement so that they could adopt it to also observe solar neutrinos, because those neutrinos are also in the same energy range. And in 1987 there was the serendipitous detection of neutrinos from SN 1987A. More about this later. And that in fact caught all the attention. Protons didn't decay, but this became one of the pioneering neutrino observatories. In 1988 they observed neutrinos from the sun. They had enough events to predict what is happening, and less than half of the expected events from standard solar model was detected, and that confirmed Davis's result that there is a deficit and therefore there is a puzzle. And this was also confirmed by much larger Super Kamiokande detector, which is actually 50,000 tons as opposed to 3,000 tons here, and it has much better precision because it has a much better coverage of the photomultiplier tubes. So the deficit is real and is not due to errors in standard solar model. So the solution must then lay in the property of neutrinos. The reason why it is not in the errors are not in the standard solar model is because that factor of half or 1/3 is too large. So if you want to reduce the neutrino flux by that amount, it will also reduce the luminosity and other factors which we know about sun, and those cannot be easily changed since they are all correlated. So therefore this deficit, the answer to the deficit must lay in the property of the neutrinos itself, and the proposal was the Ponte-Carvo's proposal, either oscillation or decay, or both were options at that time, at the time when this observation was made. So immediately after Ray Davis's experiment, Ponte-Carvo, who had proposed in 1958 nu bar oscillations, immediately turned and said that now because we know already nu mu exists, there could be an oscillation between nu e and nu mu, and that could be the result of this deficit. Why is that so? We will see here. Here is a one slide primer on what is neutrino oscillation. So the idea is that suppose there are two flavors, actually realistically there are three. Let us just take two, nu e and nu mu. They mix, and the mixture, they are superpositions of nu 1 and nu 2, and these are energy eigenstates which are propagating states, and these are flavor states, nu e and nu mu. So nu e is a mixture of nu 1 and nu 2. So because if the nu 1 and nu 2 have different masses, they acquire different phase after traveling for some time t, and this then turns out to be a mixture of nu e and nu mu as defined by this. This is the definition of the flavor states. So therefore nu e at time t will be a mixture of nu e at time 0 and nu mu at time 0, and that mixture is given in terms of this cos theta and this phase. This requires the mass of these two mass eigenstates to be different. So then you can calculate the probability of this nu e of t overlap between this and nu e at 0 mod squared, that is the probability of survival. That turns out to be 1 minus sine squared 2 theta, this is the mixing angle, and sine squared delta m squared L by 4e. Now delta m squared is the mass square difference between these two mass eigenstates. L is the length traveled, we are replacing the time by length because these are almost relativistic, and E is the energy of the neutrinos. So flavor oscillations occur when there is mass and mixing. Furthermore, because these neutrinos also interact with matter when they are, this is the vacuum probability, when the neutrinos are traveling through matter, they also interact with the matter. That interaction causes extra potential and affects the propagation of these mass eigenstates, and it turns out this is called the famous Mikhail-Smirnov-Wolfenstein effect, matter effect, in which within the matter the mixing angle is given by the mixing angle in vacuum divided by delta m squared cos 2 theta minus A. What is this A? This A is proportional to the matter density and the energy of the propagating neutrino. So since both are variable, it is possible at some stage that this A becomes equal to delta m squared cos 2 theta, and that is the resonance. This has the Breit-Wigner form, and when these two, this goes to 0, this goes to 1, which means you have maximal mixing. No matter how small the mixing angle theta is, you can get maximal mixing if the resonance occurs in matter. And the interesting thing is, if this is written for neutrinos, for antineutrinos this sign changes. So if the resonance occurs in neutrinos, in antineutrinos it won't occur, or if resonance can occur in antineutrinos, it won't occur in neutrinos, and that also depends on the sign of this delta m square, which one is heavier, which one is lighter. So this is the basic primer on neutrino oscillation physics. So what happens is that the idea is simply this, that in the oscillation scenario, neutrino changes flavor during propagation. When the mass difference is non-zero and they mix. And now when the masses are different, the phase change gives rise to a superposition of the two flavor states, even if you start with one flavor. And in sun, only nu e is produced. Now imagine nu e is propagating, it is acquiring phase. So at different points, it is different mixtures of nu e and nu mu. Suppose you have a detector which can only detect nu e. Then the nu mu part is missed and you will see a deficit. And this is precisely what happened in Davis's experiment. And you have this deficit coming into play, and oscillation seems to be the scenario which can produce such a deficit. So this will be confirmed, of course, later by Snow. It's a beautiful experiment, and Sudbury Neutrino Oscillator Observatory used heavy water, which is 1 kiloton, surrounded by pure water. It's also a small detector. It's somewhat similar to Kamiokande, but they used heavy water. Why? Because with heavy water, you can have three types of interactions. The usual nu e electron elastic scattering can happen because there are electrons, and this result checks with the should check with the results of super K, because both are very similar. And this also tells you the direction of the neutrino, because this interaction cross section is forward peaked. So you will find more events in the direction of the neutrino, and there will be a distribution around that. And the second interaction is this charge current nu e d producing E minus and pp, breakup of the deuteron, and this is only charge current, there is no neutral current as in this. So this will produce even a greater deficit and checks the results of the Davis experiment, which was only charge current. Then comes this breakup of the deuteron, neutral current breakup of the neutron. This is the same rate approximately for all flavors of neutrinos, nu d going to nu n p. And then how do you identify this interaction, because there is no charged particle in the final state? What you do is, this neutron, the recoil neutron, has enough energy and it moves through the medium and it can get captured by the proton, producing a deuteron. And the deuteron binding energy is 2.2 MeV, so there will be a characteristic gamma ray which is emitted at 2.2 MeV. And that will show that, the measuring that will give you the rate of this neutral current reaction. So the result was quite remarkable. Electron events were confirmed the deficit. Neutral current events with electron events agreed with the total flux, and the the third one, the neutral current event, confirmed the total flux, because this is blind to any flavor. So if nu E is converted into nu mu, that would also interact in the same way. So therefore, this one measures the total flux. So you are measuring all possible things with that, and this agrees with the total flux that was predicted by Bachal's standard solar model. Sorry? 2003. So the experiment was completed in 2003. They took data for 1 or 2 more years because they improved the detection of the neutron. Instead of capturing it on the proton, they introduced salt, which were neutron absorbers, and from the characteristic emissions from that, they could actually make a more precise measurement. Okay. So 150-year-old solar energy, stellar energy production issues are finally resolved. Yeah. As far as these experiments are concerned, only the flavor oscillations are relevant. Nu bar oscillations are lepton number violating. They have not been seen.
That's still, but nu bar then will not interact and produce. At least snow will close that possibility, right? That was the cause for the.
No, these solar neutrinos are all electron neutrinos. There is no nu bar.
No, if it oscillates to nu bar, and that's why Davis deficit is explained that way.
How?
And that you pointed out is a possibility.
No. Davis experiment is only nu E. It's a nu E excitation of chlorine.
Yeah, but if some number oscillates to nu bar, you will see a deficit in nu E events.
Oh, if it had oscillated to nu bar also, you would see deficit, in principle, yes.
But then you will not reproduce snow.
You will not do all the three.
Yeah.
All the three are correlated, right?
Okay.
So that will not come from nu bar oscillation. You need a separate experiment if you want to see that.
Before snow, it would have been a possibility. No, that's snow. I'm saying before snow, that would have been a possibility.
No. He's talking about Davis's time.
Before
At that time, it would have been a possibility. That's what he's saying.
That way you can explain.
That's why he's saying the deficit. If it had happened, it would have been deficit. We'll talk about it later. Yeah. That's right. That's what he's saying. Not that we have seen it. Okay. So this is no. Yeah. So here I want to move to the next topic, which is atmospheric neutrinos from solar neutrinos. So we are coming nearer Earth, and a brief history of cosmic ray research in India. I think it begins somewhere in the early part of the 20th century. Availability of great heights was an attraction, and in fact Compton led a team of researchers to Kashmir in 1926 to measure cosmic ray intensities at high altitudes. In fact, there is a very nice description of this in the Niels Bohr Library archives of APS by his wife Betty Compton, who talks about how they took mules and the detectors on top of that and climbed great heights, and how the experiment was done. Very nice. But there was no dedicated observatory. Then we have this D.M. Bose and Biba Chaudhary did some very nice experiments in cosmic rays using photographic plates. The interesting thing is that in their observation of the examination of the photographic plates, they actually find charged particle tracks which indicates that it should be about 200 times the electron mass. In fact, these papers are published in Nature. Later, Cecil Powell found the same result using the same method, and the particle was identified as pi meson or pion as we refer to it today. Then in TIFR, Baba, in PRL Sarabhai, and in Aligarh Muslim University, Professor Gill began institutional involvement in cosmic ray research, and that is where we come to this physics underground at KGF. So, yeah.
So, in 1926 there were no photographic emulsion experiment.
1930s emulsions had begun.
Okay.
And
And
that is
26
the
was
experiment. Yeah. Now, in 1926 they had cloud chamber, which they took upstairs.
those are very bulky setups.
Yeah, bulky. That's why they needed horses and other things to carry it. Yeah. So, and there's a nice description of those detectors and how they carried it and all in that Niels Bohr library oral history. So, dedicated cosmic ray muon investigations in a dedicated facility began in the 1950s in KGF by the TIFR group. This is probably the first such dedicated facility anywhere in the world, and the experiments of Miyake, Narasimham and Ramanamurthy in the beginning of 60s, at least the papers were published in the beginning of 60s, gave the function, the muon intensity as a function of depth. As you can see, they start from 270 meters underground and go all the way to 2.7 kilometers deep underground in the KGF mines, and you can see the number of counts. It keeps on going down, and counting rate per hour goes below 1 at a depth of 2.1 kilometers. So immediately they realized that when the vertical muon flux itself goes down so much, and from the sides it will be almost nil, nothing, because you have more shielding on the sides, they realized that such depths are great places for doing neutrino physics. So this was the first this thing. So they start setting up this neutrino observatory deep underground, and one of the first discoveries of atmospheric neutrinos, first major discovery from any underground laboratory, was done in the Kolar goldfields with the discovery of atmospheric neutrinos. They started setting up the experiment around 62, 63, and the first observation was published in 1965. And Reines, who actually wanted to do this experiment first at KGF, there's a backstory to this. He could not do it because it turned out that Reines wanted to keep all the complete control of the experiment with himself, and that was not acceptable to Baba and people who were already doing these cosmic ray muon experiments. So since no collaboration was possible, Reines went to South African mines where he did his experiment, and both results were published side by side and within few days of each other. So in fact, this is where you can see the first report of the atmospheric neutrinos. The paper from TIFR was published in Physics Letters dated 15th August, and similarly that of Reines was published in PRL dated 30th of August. So this is the beginning of the neutrino astrophysics, the first dedicated lab anywhere in the world. Huh? Oh, sorry. This is the KGF group. This was taken later when they were setting up proton decay experiment. This is Menon. Yeah, and Srikantan is there, and this is Nabhamandal, and many Narasimham is here. I don't think Ramanamurthy is in this picture. He had left at that time. And this is the graph of the muon intensity versus depth as it goes down. Yeah. That's right. Okay. So these were the first detectors that were set up in KGF, and the KGF underground laboratory towards the end as we are coming to 80s, had actually a total of 321 neutrino events in 1980 to 1990, out of which about 29.1 was attributed to the background. And in fact, they found these unusual events in these are called as the Kolar events, where if you extrapolate backwards, the vortex was in the air. Now, all the neutrinos which were detected in Kolar came from the rock interactions in the rock. Neutrinos interacting with the rock, producing a charged particle, which will produce a track in the detector. However, there were events which had vortex in the air, and the probability of a neutrino producing these interactions with vortex in the air is extremely small. You can see that out of these 321 events in the rock with a density of 3 grams per cc, if you extrapolate it to air, where it is 10 to the power minus 3 grams per cc, so you will not even find one event in the duration in which these detectors were operating, which is about 11 years, not even one event. But they found events such as these. In fact, there is a count something like 8 events, out of which maybe 3 or 4 have very clear vortex in the air. So the question is, what are these events? These are called Kolar events, and this problem has not yet been solved. And there is a speculation that if it's not due to neutrinos, what else can it be at this depth of 2.7 kilometers? The only other thing that can be there is the dark matter. If dark matter particle is real, we don't know what it is. But what if it is dark matter? So there is a hint of dark matter which may explain these Kolar events, or at least one of the possibilities. And well, that is the thing. And now we know, at the time when they were doing these atmospheric neutrinos in detection in Kolar, the flux was not very well known. I think the flux calculations came much later, which is why, you know, the problem with atmospheric anomaly as a deficit could not have been done in KGF at that time. So now we know that the primary cosmic rays are proton and helium, and we have these secondary cosmic ray particles, pions, which decay into muon and a neutrino, and then muon decays into electron and a pair of neutrinos, and here are the reactions that you will see. Important thing is, for every nu E type, whether it's particle or antiparticle, there are 2 nu mu's, and this ratio is 1:2. Now, what happens this is a summary of all the experiments. We are jumping to 2000. There is also an atmospheric neutrino anomaly, just as we had a solar neutrino anomaly seen in many experiments, but mainly from super K, sub GeV and multi GeV experiments. Super K has the ability to distinguish between electron type events and muon type events by looking at the nature of the Cherenkov cone, and they divide it into sub GeV and multi GeV data, and they find a deficit of 0.5 in both sub GeV and multi GeV data. And in order to eliminate the errors in the flux calculations, where there are large errors in flux calculations, they use this double ratio mu by E data as seen in the data divided by mu by E as predicted by the Monte Carlo calculations. Because of this double ratio, they are able to minimize the errors in the flux calculation. So that is one of the reasons earlier when KGF experiment was going on, this information was not available. So here is a summary of the neutrino properties, where we think that the neutrino oscillations are the answer for both solar and atmospheric neutrino properties. So this is a 3-generation realistic nu E, nu mu, nu tau mixing using this. The parameters of this mixing are theta 12, theta 23 and theta 13, along with the phase, which is actually a CP violating phase. This is the CP violation in the lepton sector, and all these parameters will have to be determined along with mass square differences, which is also unknown. So using the experimental data, one tends to estimate these parameters. So for example, angle theta 13 is approximately 9 degrees. These are from recent measurements in Diabe, Reno and W. And angle theta 12 is about 33 degrees. I think I made a mistake here. It is theta 12. And then theta 23 angle is about 45 degrees. There is no information on the phase until now. And the mass square differences, the mass difference between 1, 2 mass eigenstates is well known, 0.753 into 10 to the power minus 4 eV square. This is the one that drives the solar neutrino deficit oscillation. And then delta m squared 32, we only know the modulus, and it is 24.4 plus or minus 0.6. And this is the one which drives the atmospheric neutrino oscillations, and the sign is currently unknown. So, in fact, because the sign is not known, we do not know which is higher and which is lower, and this leads to hierarchy problem, about which I will talk a little more later. Now, there are many neutrino Nobels, as you can see, but for the very first discovery of atmospheric neutrino, there is none. So, lest we forget some honorable omissions too. Cowan passed away before the Nobel Prize was awarded. So, leave it. How much time do I have? I think half an hour. Okay. So, this is a broad review of neutrino physics until more or less 2020 or so. So, now I come to the contribution of people from IMSc. My duration is from 1980s to 2020s. And you see something, the name Indumati. She is there for 4 decades. She started as a student in 1986, and then there was a short gap in 1990s, and then came back. She has contributed, apart from other things like QCD and quantum field theory, she has contributed enormously to the neutrino physics, but I will concentrate only on the neutrino physics, and some of the contributions I won't have time to talk, which I discovered recently, because this comes from Parthasarathi, who even in 1982 itself, before oscillations were fashionable, people were talking mixing, etc., he talked about associated neutrino mixing in left-right symmetric gauge models when few took mixing seriously. So, but then that was in a very specific model, which I don't know very well, so I will not talk about it. Huh? Our Parthasarathi. So, and he also contributed to neutrino nucleus interaction in the 90s. He had a student yesterday. So, that I won't have time to talk about all those things. So, here is just a selection of these things, and this is Indumati likes muon flavored neutrinos. This was the title of an article, and as you know, Professor Indumati will be superannuating end of September this month after a research career spanning 4 decades, most of which were spent here, first as student and then as faculty after a short gap. Major contribution in neutrino physics, astrophysics, apart from other areas like QCD and QFT. So, this one is for you, this presentation. Okay, and then you can see here, freshly minted student, Indumati standing here in 1987, but you also have other people who contributed to neutrino physics. Here is Parthasarathi, here is Haridas, I will talk about him in a little while, and Debajyoti Chowdhury, with whom I collaborated on gravitational neutrino Helsinki flip. So, and there are also other students at that time, all the graduates. This is almost the whole institute in 1986, except mathematicians are not there and computer scientists are not there. The whole physics group is there. Yeah, Vaidishwaran. Okay. Sharat Chandra, Vaidishwaran, Rahul Basu, Date. Huh. Yeah. So, okay. So, one of the first things that happened in the 80s, 86, in January, Indumati joined, and I think Ravindran came in July. Yeah. So, Indumati came and brought this cataclysmic event, which is a supernova SN87A within a month. Okay. So, that happened. And Haridas was the only one who knew anything about supernova at the time, and we used to get the information from the IAU telegrams, and those telegrams used to come to Raman Institute, and Haridas had contacts in Raman Institute, so he used to get that information, and we used to get that whole information from the telegrams within a day or so. That is how we were able to latch on to this problem so fast. And since Haridas also had knowledge of stellar collapse and some extent also the neutrino emission, we all sat down, and for the next 2 weeks immediately after this explosion there was nothing but just this work all 24 hours among the 4 of us. So what we did was we did a critical analysis of the events from Kamioka. Kamioka observed neutrinos from SN18. By the way, this was the first observation of neutrinos from supernova. Earlier supernova observations were all optical. This is the very first set of events where neutrinos from supernova were detected. And it's the only one, but it's likely to happen more frequently because we have neutrino detectors. Okay? And it coincided with optical, but there is a difference. The optical curve actually starts as a faint thing and then increases. There is a peak after 24 hours and then it goes down. Whereas the neutrino emission just happens.
So that will put a bound on neutrino mass.
Well, we'll come to that.
Okay.
Yes.
Velocity of
yes, you're saying what I am going to say. Okay. But the thing is, the trigger for any supernova thing will be neutrino, not the optical, because optical takes time to build up. Yeah. So this was the first observation of neutrinos from any supernova, and the events were recorded at the Kamioka, same place where we saw the solar events, and IMB, Irving, Michigan and Brookhaven collaboration, and Mont Blanc. Mont Blanc recorded the events 4 hours after Kamioka. So that is almost impossible because as you will see, I'll show you, neutrino emission takes place above the detector threshold within 1 second. So it's almost impossible to get 4-hour delay in the events. So we can rule out Mont Blanc as unlikely, and IMB was questionable because even though they had something like more than 10 events, the average energy of those events were much higher. They were in double digits, which is rather unlikely from the supernova, this thing. Maybe few events could have been due to supernova. On the other hand, Kamioka had a very clean set of 12 events which could be attributed to the supernova, and the timing also coincided. So they had, there was some problem with timing which they adjusted later and confirmed it. So we analyzed the events from all these 3 observatories, ruled out Mont Blanc, and IMB we could not include in our analysis because we didn't think that they were, at least all of them were not the neutrino events from SN87A, and so we seriously analyzed the 12 events which were recorded by the Kamioka Observatory using the models of neutrino emission of Burroughs and Latimer and Wilson, etc. So what happens in a supernova emission is that, as many of you heard in the morning, the first neutrino emission, which is called as the burst neutrino, happens during the electron capture. The electron is captured on the proton and then it gives rise to neutron and a nu e. These are called as the burst neutrinos. This is the neutronization phase where the hot neutron star is getting richer and richer in neutrons. It is yet to become a neutron star. So then once the K capture phase is more or less done, you have the cooling phase, and because the star has really collapsed to a very high dense state, even though many interactions are taking place, the only way for cooling this is neutrino emission, because the only neutrinos can stream through this high dense matter and nothing else can come out. So the thermal phase is dominated by neutrino emission, and in fact almost all the binding energy of the neutron star, which is about 10 to the power 53 ergs, comes from the cooling phase. And this is the binding energy of the neutron star for a collapsing star of mass greater than at least 8 solar masses. It may be larger than that. So we discussed all these possible observations of burst and thermal neutrinos sequences in the Kamioka events, and then assuming the delta T at emission, the cooling phase actually lasts more than 50 seconds, but within 1 second the energy goes down exponentially, so that the threshold of our detectors is few MeV, and the neutrino energy goes below that within about 1 second. So what is relevant is the neutrinos emitted in the first 1 second and during the burst phase. So that we discussed, and using the time delta T in the observation, we predicted that there is a spread, and this spread could only come from the massive neutrinos because there is time dilation. It doesn't travel with speed of light. So using that, we calculated the limit on the neutrino mass to be 25 eV, and this was published in this paper at Current Science, June 20, 1987. It was submitted end of March. Now that's a story I might be able to tell you. So here are the analysis. Here is we take the model of supernova neutrino emission as was known on that day. Now today you have much better models. So this is nu E going to nu E. These are the burst neutrinos. We estimated that it will be not more than 1 event out of the 10 events that you see, and this is emitted in 0.2 seconds. 0 to 1 second is the total duration, and then you have the anti-neutrino events. Now in the case of supernova, it is not just electron neutrinos. Only electron neutrinos come only during the burst phase because of K capture. During the cooling phase, the neutrinos are pair produced. For every neutrino, an anti-neutrino is also produced because you have to conserve the lepton number. So therefore nu bar pairs of all flavors are produced during cooling phase, and the nu E bar electron, the number of events will be small, but the main contribution to the event comes from nu E bar P going to E plus N, and there are 7 events using the flux calculations given by the models. Now this gives you about 8 events, and that is comparable to, in the case of, even though there are 12 events, out of those 12 events I think 2 events can be rejected, and we have 9 or 10 genuine events, and our calculation gave the events to be about 8, which is a very good thing. You know, we are not using any other fancy thing. We are just using the flux, the distance, how the flux gets reduced, the cross sections, interaction cross sections, and why there are 7 events here, even though the number of nu E and nu E bar may be the same. This is because the cross section of nu E bar on protons is about 10 times the cross section for nu E on E. Nu E cannot interact on P because it's not possible to produce the final state. If it's a deuteron, that would have been done. So this is the events, and here is, you see, all the neutrinos are emitted within 1 second. That is this dashed line. But the events have been seen over 12 seconds. So how do you explain this thing? So if you assume m nu of 25 electron volts, then you can get a spread from 1 second at emission to about 12 seconds at absorption. Now this was one of the best limits on neutrino mass available in 1987. There was a limit from the Russian group which was about 32 electron volts. That was experimental, and this was better than the direct limit we had at that time. But of course there was also a theoretical limit from indirect cosmological considerations. This is by Kausick and McClellan, and so this was one of the first ones to put such limits from observations. 25 eV here. Yeah.
Produces the neutrinos, but how come that's not there in this?
That is this
table?
burst neutrino. No, these are interactions, the detection. At the detector,
at the detector,
what are the
I see.
things?
Okay.
That is at the production.
Okay.
Okay. Yeah. So neutrino physics at IMSc, we'll let me quickly go through 15 minutes. Okay. Yeah. So Rajaji's, I'll quickly review some of the things and then go to some other important things. So Rajaji suggested that at that time he was more or less leading the group, and he suggested that we should focus on Bethé's paper on the application of MSW effect to solar neutrinos, which had just come in 1986, and he said it should be done in realistic 3 generation, and that was immediately done. And also there was another group, Kuo and Pantalriene, who also did it. And then we, in the 1994-95 time, we did a complete analysis of all the data, both combining solar and atmospheric neutrino data in the realistic 3 generation. And I think in all these things we were probably before the other groups around the world. And this was extended to day-night effect by Balaji, who was a student of Rahul Sinha and Rajaji. And interesting work on eclipse effect, where the matter effect plays a role. That was done during the, that was done by Mohan Narayan, Rajaji, Rahul Sinha, and C.P. Burgess. Am I right? Yeah. Okay. So these were some very interesting things, but all these were done in the realistic case of 3 generations. We made it a habit. We do everything, no toy models anymore, because we know enough from the data, so we should do this. Okay. So then one very important and notable contribution came from this institute, though not recognized very well, is the analysis of the Choose reactor neutrino data in 1997. They showed that the third mixing angle θ13 is less than 12 degrees, and this was confirmed by Diabe and Reno in recent experiment, who have improved this. And initially, when the Choose data came, the first version of their paper, they had done this toy model of 2 generation calculation and arrived at wrong results. So immediately Mohan Narayan, Rajshekaran and Uma Shankar, they had already done the 3 generation calculation. They showed that this experiment is very important, because it for the first time shows that θ13 angle has to be very small. And in fact they put a limit of 13 degrees at that time, and they communicated this to the experimentalists, as far as I know. And the experimentalists changed the in the second version of the Choose data, Choose paper, they actually had the correct limit on θ13 in the 3 generation thing. The sad part was that there was no acknowledgement of any kind to the work of Mohan Narayan, Rajshekaran and Uma Shankar. So Rajaji of course did many things using the fact that θ13 is small. What if θ13 is 0? Usually such things happen in the symmetry limit. So what kind of a symmetry can drive θ13 to 0? So they created a model of neutrino mass and mixing, which is based on A4 symmetry. This is a very popular paper. I can't go into the details of this paper. Then they had a new mechanism for generating neutrino masses. This was done in collaboration with Divakaran. And RG evolution of applying renormalization group evolution to evolve the parameters from very high scale to the low scale, so that we can understand why they are so different, why these angles are so different. You start with a symmetry where all these angles are small but they may be equal. They showed that RG evolution backwards to the lower scale can actually create those differences. Then comes the realistic supernova calculation. This was done by Indumati and her collaborators, and the cooling phase, as I said, involves nu e, nu mu, nu tau and their antiparticles. So a realistic 3 generation framework, once again this was also one of the first calculations to do this, with mixing and oscillation incorporated. This was done. Event rates were analyzed for a water Cherenkov detector if the supernova explosion happens at a distance of approximately 10 kiloparsecs. Why 10 kiloparsecs? If it happens in our own galaxy, it will be at maximum distance of about 10 to 20 kiloparsecs. Now, even if you cannot see it optically, which is difficult if it happens in our own galaxy, you will see it through neutrinos. Now, the neutrino observation becomes more important. So, therefore, we took that distance and we looked at, we had a very nice prediction. I will show you in the details in the next slide, where that effect of mixing can be seen in events which have a distinct experimental signature, since they will be backward peaked, and these backward peaked events are signals of the mixing and oscillation. I will say something more soon. Continuing the same scheme, same theme, compared signatures of water and heavy water detectors and possible effect of sterile fourth generation impacting the neutrino emission. So, what did I mean by this? This is a very nice prediction, and I think just before us, Vic Haxton from Seattle had a similar prediction, and probably we also saw it and then worked on it in greater detail. So, here you can see that these are the detectors, 1 kiloton no oscillation, 1 kiloton maximum oscillation, and super K no oscillation, maximum oscillation. And what is the detection mechanism? Nu 1, this is L can be E mu or tau, scattering elastically on electron, and nu E bar interacting with the proton producing N and E plus, and nu E interacting with oxygen 16 producing E minus and 16N, and then nu E bar doing it on oxygen 16 producing fluorine. Why these are important? Normally these reactions cannot go through without oscillation. That is because these have a higher threshold of more than 10 MeV, and normal average energy of nu E is less than the average energy of nu mu and nu tau. That is because nu E interacts much more because it has both charge current and neutral current interaction, whereas nu mu and nu tau have only neutral current interactions. So, they thermalize at different temperatures. So, since the temperature for nu E is lower, its average energy is lower, it is around 8 MeV, and that is not sufficient to trigger these reactions. But nu mu has an average energy of 15 MeV. Its temperature is around 5, and then if you assume Fermi gas, it's 3.15 times temperature is the average energy. So, if you do that, you get about 15 MeV. Now, if these nu mu's are converting into nu E's, then those nu E's can trigger these reactions. And why is this important? Here these electrons predominantly, electron and positron predominantly come in the backward direction. Now, since you know the direction of incoming neutrinos, if you see more events in the backward directions, more than without oscillation, then that is a signature of nu mu events produced by nu E after conversion, or nu E or nu E bar. This is a very solid prediction. In any next supernova, if it happens close enough, then you can see, and in fact it is quite dramatic. For example, in super K, no oscillation is 30, maximum oscillation is 761 number of events. So, similarly, if this is for E greater than 8 MeV, that is the kind of difference, and even in nu E bar you will see some differences in oxygen events here, 123 to 260. So, this is the most dramatic one that you can find, and usually neutrino spectrum in supernova goes beyond 30 MeV also, up to about 50 MeV it goes. So, we have separated 8 MeV and 30 MeV. Below 8 MeV there will not be any events on oxygen that you will not be able to see. So, it is pretty dramatic signal. We know the direction of supernova, no? Yeah, the optical this thing, and also this elastic scattering is there, no? Nu E going to nu E. This carries the signature of the direction. Okay. Yes, because nu E gives you the direction, so you can see where the supernova is. So that neutrino astrophysics is fantastic that way today. We have fantastic detectors, we can actually do it. And anomalous polar events, I just mentioned it earlier. Basically, Also that there are some proposed experiments at the new ICAL detector, which at the moment is in hibernation, but this was also done by Rajaji, Datar, Indumati and Satyanarayan. So I will mention 5 minutes. Okay. In the Neutrino Observatory, I mean, this is where I think Indumati has spent nearly 2 decades working with a tribe of students and a huge number of students. And the idea got off the ground in 2000 during WEP meeting here, which happened. And the group worked tirelessly on all aspects of INO, active participants in science, R&D, site survey and selection, especially also the public outreach. The main detector was iron calorimeter, magnetized iron calorimeter, with the goal of establishing neutrino mass hierarchy. I will tell you what it is. Project was approved in 2015, but physics issues, R&D completed for the ICAL detector. Prototype was mounted. In fact, mini ICAL was designed by Vivek Datar, who is sitting here. Nearly 50 students got their PhD and they have been placed all around the world except in INO. And the graduate training program involved both experiment and theory. And this is what I mean by neutrino hierarchy problem. You don't know the absolute masses of these neutrinos, M1, M2, M3. These are the mass eigenstates. The ordering could be, given the present experimental results, it could be M1, M2, M3, or it could be M3, M1 and M2. Now this is called the normal hierarchy, this is called the inverted hierarchy, and there are some implications of which hierarchy, and that has implications for various other aspects of including cosmological implications. I will not go into that. So in order to but how do you see this hierarchy? I mean, what is it that you can measure which tells you what the hierarchy should be? And this was worked out in a paper by Indumati. The asymmetry is defined as up by down of muon neutrinos minus up by down, up events by down events, up events by down events with nu mu bar. So you need a detector which can distinguish between nu mu and nu mu bar. That is possible only in a magnetized detector, and that is why the magnetized ion calorimeter detector was chosen. And the asymmetry is a function of angle theta 1 3 and length divided by energy. This is so what you have is L by E, and what you can see here is, it's important to know, this is the theta 1 3 no, this delta is the mass square difference, and theta 1 3 we have chosen to be 5, 7, 9 and 11. So what you see is that this asymmetry is completely out of phase depending on whether it is inverted hierarchy or the direct hierarchy, normal hierarchy or the inverted hierarchy. This totally completely out of phase, precisely out of phase, is a signature of, I mean, it provides information about whether it's inverted hierarchy or normal hierarchy, and this led to the main goal of defining the main goal of ion calorimeter detector, and also detectors many places around the world. The hierarchy question was taken up by the Chinese experiment Juno and also Dune in US. Yes, correct. So what happens is that the downgoing neutrinos provide a baseline because no oscillations. I mean, it's a very short distance. Whereas the ones which are coming from down not only oscillate, but they also involve matter effect. It is the matter effect that is important in distinguishing between normal and inverted hierarchy. I didn't go into the details there. So this hierarchy is also one of the aims of these detectors Juno and Dune. And one of the observations that was made in this paper was that since there are many unknowns, there are always degeneracies. You have to assume something in order to find something. So these are called degeneracies. So for example, CP phase is not known. So how do you know hierarchy can be established without knowing the CP phase? Because CP phase is also sitting there. It turns out that in this calculation, it was shown that this hierarchy estimate determination is independent of the CP phase. I think that was a very crucial thing. It has not been noticed very well, but the fact is that it is independent of the CP phase. It avoids the degeneracy problem. Okay. So with this established, IMSc group analyzed the sensitivity. Then we went into the details of the sensitivity of such a detector, and this sensitivity was to not only to the parameters but also to the matter effects, and how matter effects change even if we change the parameters of the earth structure a little bit. A very detailed calculation was done. This was done by Indumati, Rajaji, Neeta and me, and and also Neeta and Indu worked on this tau production and signals of tau decay. See, tau decay also produce muon neutrinos. So therefore, there will be a background to the muon events from the tau decays. So how to separate them? There is always a time lag, so one can use that, and all these were addressed by Neeta and Indu, and in fact that went into the as a part of the white paper on neutrino factories. So, and there have been many students trained by Indumati. Here is a complete invited review of the physics potential of ICAL at Indian. It's a very detailed thing, and I have marked all the students who worked with IMSc group, especially with Indumati, actually mostly with Indumati. So she has trained huge number of students, okay, and most of them have completed, all of them have completed their PhDs, and many of them are postdocs, some of them even have jobs, etc. So then I will skip this. As opposed to determining hierarchy without CP dependence, recently we also did the opposite, hierarchy independent determination of CP, again avoiding the degeneracy in the other direction, and this was done in 2019. It's actually a very straightforward paper. I mean, at least to me it was a mystery why it was not noticed all these years, and in fact the referee comment was that what is the big deal, it is so. But then we told the referee that it has not been said so. You have to do the calculation and show and how to determine. So this was nice. And another thing about this paper is that this paper grew out of our, what is this club, journal club in IMSc, which was started by Ravindran. And so journal club has given rise to many papers like that. So that was nice. Low energy. At low energy, what you can show is that if you choose correctly the distance or correct L by E ratio, then the terms involving that delta M32, which is only the modulus we know, those terms can be averaged out. The moment they go, delta M21 is very well known from solar, and theta 12 is very well known. So therefore, you have a very neat determination of delta, and in fact you don't have to do a new experiment. SK, which is collecting the events, will have enough statistics in probably another 10 years. So you just wait it out. As long as it's taking data, at some stage you get the statistical significance and you can determine phase. Yeah. Right. Yeah. In fact, there is an asymmetry that we have defined there. Okay. So I'll skip this because I have talked about this already in IMSc before. It's more detailed. So here, last slide. Okay. So we have windows to the future here, in the neutrinos. Even though I have said that we have solved many things, there are many other problems which are still remaining. So observations of neutrinos, non-zero mass and mixing, opening a window to the physics beyond standard model. There are still many open problems. The sterile neutrino, are they there? See, this from the unitarity constraint you can find out whether there is sterile neutrino or not, because the mixing matrix is unitary. So if with 3 generations you cannot satisfy the unitarity constraint, then there has to be one more. So from the limits that we have, we can actually see what kind of 4th generation or higher generation is there. So origin of neutrino mass, Higgs mechanism, CISA, we don't know. And what's the nature of neutrino? That was there in the previous. This you can determine using Pauli principle, going beyond double beta decay. It is possible, and that work was done by Kim, Divya Kripa Sahu and me. It was published about 2 years ago. And then from astrophysics point of view, complete neutrino spectroscopy of the sun is yet to be done. We need new experiments. And one of the proposals is the deuterated liquid scintillator, on which we are all working. Vivek Datar, Indumati, Basudev Das Gupta, and several people from TIFR, his postdoc. We are all working on this. This needs a proof of principle, which has to be done in a place where experimental facilities are available. But this appears to be one of the most promising ways towards these precision measurements of solar, supernova, and geoneutrinos, complementing the ongoing and planned experiments worldwide. So here, the moral of the story is, if we have a story to tell, we must tell the story loudly, honestly, and clearly. So I'm not sure whether I'll be coming here to give more talks, so I'll take this opportunity to acknowledge and thank my collaborators, Indu, Ravi, Rajaji, Shankar, Shyam, for a lifelong learning and collaboration, and just for the joy of doing physics. Thank you very much.
Any further questions? Yeah.
What it can do, that experiment under, I think it can also detect neutrinos from gravitational wave events, right? Neutron star merger that they tried during the LIGO event. So if you say that, it would be very interesting, right?
It depends on what the energy is. If it's very low energy, as such this deuterated liquid scintillator cannot.
Okay.
But there are ways of putting salt into that. There are, what is that salt? Gadolinium. Gadolinium, this thing. Then you can go to very low energies. That is what I meant by doing precision spectroscopy.
So you are planning to put the salt or not?
No. Right now nothing has started.
Okay.
But the calculations and some physics goals of such a detector are being worked out by the group.
Actually answer that. The lowest threshold, zero threshold, is the plastic scattering of electrons. And the advantage of such a scintillator would be, in addition to, of course, measuring neutral current events, that is, of course, the main USP, but you would get a signal which is about 50 times the Cherenkov signal. So, the confidence level, that is much better, the resolution. Whereas, as I said, Cherenkov, of course, Cherenkov has the other advantage that you have directionality.
Yeah.
Whereas, so that anyway would be there even in this to some extent. The scintillation, of course, would be there. Cherenkov plus scintillation. Or whether one would be able to decipher this from that. Okay, that is a matter of principally it may be possible.
Yeah.
What is the status of the mixing angle in the neutrino sector? How well it is known, and what is your insights on how well it can be improved?
Theta 21 and theta 23 were reasonably well determined. I showed the numbers. Theta 13, we had a limit from the Chu experiment earlier, but now they are well determined. They in fact, it's a serendipitous thing. In our calculation and hierarchy, we use 9 degrees. But today, theta 13 is, the central value is close to 9, plus or minus, I think about...
It is best determined of all.
Yeah. So the angles are very well determined. Delta M21, the solar mass difference, that is very well determined. But the 3-2, the hierarchy, that is the open problem. And then the phase. Modulus is known, but sign is not known. Then you have the phase.
And the phase is not very well. Are there any experiments which are trying to measure?
Yeah.
Actually, there is a Kamioka experiment which is indicative of a non-zero
phase.
The CP is violated.
Yeah.
But it is, I think, at the 2.5-3 sigma level.
No, but it is in contradiction to the T2K which has. So there are two experiments which have seen the CP phase, and the two are in contradiction where there's a 3 sigma tension between them. So I think it will just need more data.
That is very important for leptogenesis.
Yeah.
Are there any plans in India for those, or for measuring the phase? Vivek, maybe?
We need a lab. We need a lab where the experiments can be done. So we need a hole underground which is deep enough, and then all these things can be done. The moment you give a space, there are so many ideas which can be executed in such a place. Not just physics, not just neutrino physics. You can have geophysics, you can have...
There was this Jadugoda mine experiment.
That's not deep enough.
There is actually a paper on dark matter. There's a dark matter search using a very novel kind of detector, which is one of which is there in snow. That's it.
Actually,
That's only 800 meters. Yeah.
No, 570.
550 meters.
550.
My maximum depth is
550.
800.
Maximum is 880.
Right now, Mala is at 550.
Mala is at 550. Right?
Yeah.
there was a Chinese experiment after our they came up with similar things.
Oh, Juno has started taking data.
Juno started taking data.
They just a few months back they started taking data, and if ICAL had been, if we had gone through without any problem, it would have been at least 2 to 3 years of data taking would have been over. We would have been, we were very much ahead of the curve. They started in 2007. They started in 2000.
Yeah.
So,
actually, by 2012, I remember that they were still planning on what kind of detectors.
Correct. They
Yeah,
were.
because I attended a talk.
They were putting together all the sensitivities and other things. But they have started.
That was not the one that finally implemented.
Dune also will probably start in another 7-8 years, but they may have some problem with funding now.
I want to make a mention about what Rahul was asking. In 2013, I was in Beijing, and I gave a talk on INO, including the hierarchy, and I think only then they appreciated really what the mass ordering problem was.
Yes.
And then after that only they took Juno very seriously and started looking at ways to actually measure the hierarchy. So maybe I'm responsible for...
Well, you inspired them. How does it matter who measures?
Somebody has to do. True. Yeah, we had some 4 hours of discussion on. They were trying to understand what actually the problem was. So.
Short question, comment. Suppose some rich donor wants to give you money.
It's not the money,
No. Money is paid. How much money will you need?
Oh,
2,000 crores or more?
No. That depends. Suppose we have a place. Now, when we started, there were no tunnels in India. Today, there are so many tunnels that are being built left and right. If there is a suitable tunnel which has enough cover, then the actual construction cost will come down enormously. So then it will be the cost of the detector. And I don't know how much DLS
What is the
costs.
maximum, roughly? What is the maximum you need?
1,532 crores was sanctioned by the government.
At that time, probably with that we can do, right?
It is not the money. There is plenty of money. It is the location to build the land. Because the government
Okay, understand.
The government which gave the land free of cost
But suppose
has now opposed the project,
but
right?
suppose some private donors give you land.
No, you cannot do that. No. You need clearances from the government.
Okay, that's the issue.
You need permissions you need clearances from the government, and the government,
These
this is the same government which gave you permissions and gave you the land free of cost for doing this experiment, has now opposed the project, right? So.
Thank you.
Okay, any other questions? Okay, if not, let's thank Murthy for a very nice talk. So we meet again at 20 minutes, 3:55.